So we've motivated the definite integral. What is the definite integral? Well, let's find out. We're going to let f be a function defined on the interval from a to b, and we will subdivide the interval from a to b into n intervals of length delta x, which is b minus a over n. We will choose sample points xi star, where I ranges from 1 to n, every single whole number from 1 to n, from the different subintervals. So xi star is from the ith subinterval. For example, x1 star is from the very first one, x2 stars from the next one, etc., all the way up to xn stars from the last one. And we define the definite interval of f of x from a to b. So this depends on f, a, and b. So f of x in the interval is defined to be the following if the limit exists. It's this expression here, and I'll explain what that means and how we read that. But this expression is the definite interval from a to b, and it's equal to the limit as n goes to infinity of this sum right here. Now this sum right here is one of our approximations. It's the sum over the intervals of the function evaluated at a sample point in the interval times the length of the interval. Remember, we saw this in the context where this was the height of a rectangle times the width of a rectangle, so it gave us an area. We saw this in the context of this being a velocity and this being a time interval, so this gave us a distance traveled. And in the problem sets, I suggested some other ways that we could look at this. In terms of interest theory, the physical concept of work, etc. So in any case, this was a sort of quantity that kept coming up, and we liked this idea of getting better and better approximations by letting n get bigger. And so we're just saying, as we let n go to infinity, if this actually approaches some specific number, then we're going to call that the definite integral from a to b of f of x. Okay, so let's sort of parse this notation. This is a lot busier than the notation for differentiation. So here we go. First we have this sort of long, skinny s. That's called the integral sign. And it really is supposed to look like a long, tall, skinny s. It kind of stands for summation, because the idea is that the integral is sort of like a sum, adding up a bunch of things. But whereas what we were looking at were finite sums before, where we were adding up a finite number of things, an integral, in a sense, is kind of adding up an infinite number of things. We're really adding up the value of the function over every value between a and b in some sense. But that's not quite exact. Okay. A and b are called the limits of integration. A is the lower limit, b is the upper limit. They tell us where we're starting the integral and where we finish it. F, the function, has a fancy name. It's the integrand. It's the thing that we're integrating. And this dx here is called a differential, and it doesn't really mean anything to us yet. But there are a couple of things that you could sort of imagine it to be, let's say. First, dx tells us what we're integrating with respect to. We're integrating with respect to x. X is the independent variable. We're integrating with respect to that. So, this is not really going to happen in our class, but if we had a couple of variables floating around, this would say integrate with respect to x, not anything else. Additionally, dx kind of plays the same role that delta x played in the sums for our approximations. So here are some basic facts about integration. First of all, the definite integral for positive functions f does give the correct notion of area under f of x above the x-axis and between a and b. So this area right here, assuming the integral exists, is indeed equal to the integral. Great. Second, in general, if you have a function which is not always above the x-axis, if it's above and below the x-axis, then the integral still can be interpreted as an area. However, it's a quote-unquote signed area, which means that areas above the x-axis are counted positively. Areas below the x-axis are counted negatively. That's just because when you're below the x-axis, the value of the function is negative. So when you integrate over this piece, you end up with just negative function values and therefore negative integral. In any case, if we integrate this function f of x from a to b, this region A and this region C lie above the x-axis, so they get counted positively. This region B lies below the x-axis, so it gets counted negatively. So the integral from a to b of f of x dx here is a minus b plus c. Finally, if f of x is continuous or has a finite number of jump discontinuities, that means it's like a step function, just a couple of places where it's discontinuous, but just it doesn't go off to infinity or anything weird or oscillate forever, then the integral always exists. So this pretty much means that no matter what function we're dealing with, most of the functions we're dealing with are continuous or have maybe a finite number of bad spots. And so great. Integrals for those functions always exist. So first, let's evaluate the integral from 0 to 1 of the square root of 1 minus x squared. Well, the square root of 1 minus x squared, that is the graph of the semicircle of the unit semicircle lying above the x-axis. You can see this by setting y equal to the square root of 1 minus x squared, squaring both sides, adding x squared to both sides, and getting x squared plus y squared is 1. It's a circle. So, we already know that the area of the entire unit circle is pi. Half of the unit circle, a semicircle, would have area pi over 2. But we're just looking at a quarter of the circle because we're going from 0 to 1. So that means that this area over here is pi over 4. Great. Now we're going to take the integral of x minus 1 from negative 2 to 3. So here's x minus 1. Wow, that's not that great of a graph, Professor Bright. Anyways, so you can graph x minus 1 from negative 2 to 3. Well, this graph looks like two triangles. There's part that lies above the x-axis, part that lies below the x-axis. So this area down here will get counted negatively, and this area up here will get counted positively. This is a triangle with base 1, 2, 3, and height also equal to 1, 2, 3. So its area is 3 times 3 divided by 2. And since it's below the x-axis, we're going to count that negatively. So this is equal to negative 3 squared divided by 2. Whereas this triangle is above the x-axis, we count its area positively. It has base 2, it has height 2, so its area is 2 times 2 divided by 2, 2 squared over 2. This works out to negative 4.5 plus 2, which is negative 2.5. So these examples aren't super enlightening, but at the very least, I think what they're showing is, okay, integrals are areas. If we know the areas, we can at the very least compute the integrals.